Based on the TimeGAN paper, let's break down the main blocks of code, the neural networks to consider, and their training loops. We'll look at how to train them individually and then jointly to achieve a generator of synthetic data that is sufficiently realistic. In the original paper, the authors mentioned that they have used about 15 years of daily Google stock prices. They have used as features the open price, high, low, close, adjusted close, and volume. Aside from the volume, these are practically the same plot. It's essentially like having the same dataset repeated 5 times with some noise. So personally, I find this a bit strange, but there is no further clarification about this in the paper. I have seen other implementations where different stocks from the market are used as features of a time series to train a TimeGAN and generate synthetic data. However, using different stocks with distinct behaviors as features doesn't seem very logical to me either. Since, for example, the cyclical pattern of a mining stock has nothing to do with the behavior of a food or technology stock. So, in order to find the middle ground, we will use the prices of the 7 most traded major cryptocurrencies as data, aiming to select a time period where there is no clear manipulation from whales or critical events happening. In this way, we have a time series with 7 features that represent very similar buying and selling patterns from retail traders. This is the TimeGAN structure that we need to implement. So let's get started. First, we need to import the necessary modules and load the data. The data consists of cryptocurrency prices, which were fetched from Binance using their API. We can plot the data and observe that they tend to follow some kind of similar pattern. Next, we can check the correlation between the different cryptocurrencies. We can also plot this correlation. And since the prices are on a very different scale, we need to normalize the data. Finally, we need to create our samples, which will consist of 24 time steps, with each time step containing the price of the different cryptocurrencies. So we are going to run rolling window sequences. Each sequence is going to have 24 time steps, and each time step is going to have the price of each cryptocurrency. So we perform the rolling windows and we have our dataset ready. Next, let's take a look at the TimeGAN structure. Here on the left, we can see the Autoencoder network, where we go from real sequence, embedding into a latent space, and then with the recovery network, we get into the original dimensions. And in the right, we've got our generative adversarial network, with its generator and discriminator. During training, we have to provide real data samples and also random samples for our training. We can achieve that using TensorFlow's dataset methods to load the data, combined with Python's iterator function. This way, each time we call the iterator, we get a new sample for our real dataset and also for our random dataset. We can see here the random iterator. We will also need the placeholders for the real data and the random data. We define them just here. And next, we are going to define the components and neural networks. In this overview, I'm using fairly simple recurrent neural networks to build the main structure. However, once the data is processed, and depending on the nature of the data, these networks can be adapted as needed. Here we've got our embedding layer, the embedder. It's a pretty simple recurrent neural network, just with some GRU layers. And the embedder will increase the dimensionality from 7 features to 24 in the latent space. The embedder's network's role is to transform the input data, which in this case has 7 features, the prices of 7 different cryptocurrencies, into a higher dimensional space. Specifically, it will take those 7 features and increase the dimensionality to 24. The reason we do this is to allow the model to capture more complex relationships within the data. By embedding the data into a higher dimensional space, we give the model more flexibility to learn hidden patterns or structures that may not be immediately obvious in the original 7-dimensional space. We move to the recovery network. Also pretty simple, and we can check that we go from the 24 dimensions of the latent space to the original 7 dimensions of our original dataset, the 7 features. So next we go to the generator, also a simple recurrent neural network. We can see here, which uses a random noise sample to generate a synthetic sample with 24 dimensions in the latent space. As we can see, the input to the generator is a random sample with 7 features, and it outputs a sample with 24 dimensions in the latent space. A way of thinking about the latent space could be like increasing the amount of adjectives to describe something. If you go from using only 7 adjectives to use 24 adjectives, you can catch more subtle information in your description. Okay, next we have the discriminator, which input are the 24 dimensions of the latent space, and as output only one neuron, used to predict if the data is true or false. Next we have the supervisor, which operates in the latent space, and its role is to ensure that the temporal dynamics of the data are preserved, as we will see later. Next, we are going to build and train the autoencoder. We can see better the autoencoder here and its function. Let's define H as the real sample going through the embedder, and then this H is going to pass through the recovery network, and we will have X tilde. So our autoencoder will consist of a real sequence passing through the embedder into the latent space and then being reconstructed by the recovery network back to its original dimensions. And we need to perform an initial training of the autoencoder so that we get a decent representation of the data in the latent space before integrating the adversarial training. We define the training step using the gradient tape, so during the forward pass, all operations are recorded. This allows us to compute the gradients using tape.gradients with respect to the model's parameters, which in this case are the embedder and recovery trainable variables. And after computing the gradients, we use the optimizer to apply those gradients and update the model parameters. Okay, the next step is training the supervisor. Here we've got the supervisor network. And we will take a real sample, pass it through the embedder into the latent space, and train the supervisor weights so that the future steps predicted by the supervisor are as similar as possible to the original future steps in the latent space. This process is what the paper refers to as capturing the future temporal dynamics. And why do we enforce this condition in the latent space rather than in the original space? If we applied it in the original dimensions, we would only force the supervisor's output to match the original data directly. However, in the latent space, we have a higher dimensional representation of the data that captures more detailed and abstract information. This is what we focus on, the more extensive representation in the latent space, which holds more information about the patterns in the data. As an example, imagine a data sample of whatever represented on the 3D space as a 3D vector. If we paint another 3D vector close to this one, we will end up with almost the same vector. But if we transform the original vector into a higher dimensional space, and we find another vector close to it in this high dimensional space, they will be similar in a richer amount of characteristics, despite of maybe being different vectors once back to the 3 dimensions. Next are going to be the blocks for the joint training, needed for training all blocks together. We will have an adversarial network with supervisor, which is going to be this path, pinky path, and also an adversarial network without the supervisor. You can see with the supervisor we go from a random sequence into the generator and we go into the latent space through the supervisor and then through the discriminator to check if our data is real or not. And the adversarial network with no supervisor, which is going to be almost the same path, the blue one, from a random sequence into the generator, latent space, and through the discriminator we classify our data without going through the supervisor. And okay, we will have to alternate between training the adversarial network with and without the supervisor. And why? Okay, we need to achieve a balance between generating realistic data when we do not use the supervisor and also ensuring that the generated data follows the correct temporal dynamics. We ensure that when we use the supervisor. So, next is going to be the synthetic data model. To generate synthetic data from a random input, we can see the path that it follows here. So we go from a random sequence into the generator, latent space, go through the supervisor, and then recovery from the latent space dimensions into the original dimensions. So we generate synthetic data from random sequences. Next is going to be the discriminator model. The discriminator model, as we can see here, is going to flow from the real sequence into the embedder, latent space, discriminator, and classify. Now we are going for the generator train step. We are going to use 4 networks with their loss functions. We need to define a new function called the getGeneratorMomentLoss to measure how well the generated data matches the statistical properties mean and variance of the real data. By reducing this loss, we ensure that the generator is producing realistic data that matches the distribution of the real data. Without minimizing this kind of loss, the generator might produce data with the correct structure or appearance, but with the statistical properties far away from our real data. We are going to use it during the training process in such a way that x hat, originated from random data zeta, is always going to be pushed to have similar variance and mean as the real data inputted in X. So, the train generator step is going to take 4 networks. As you can see here, one network, you can see the path, another network, you can see the path, another one, and another one. For each of them, we calculate one loss. We combine all the losses and apply gradients to minimize that losses. As we can see here in the train generator step, the first network is the adversarial supervised. We are going from fake data, zeta, through the supervisor into y fake, and we measure the loss. The loss is going to be comparing the result we get versus getting all ones, y all ones. We are going to measure how far our fake data is going to be from producing a real result. The next network is going to be the adversarial not supervised, this kind of blue-violet color. We are going to measure also its loss. Again, we are going to compare our result against having a result of all ones. Next is going to be this path. We are going from real data into the supervisor, so we keep on training again the supervisor. We did already at the beginning with real data. We keep on training it, of course, with real data. And the last step is going to be using the function we mentioned before, get the generator moment loss. So we are going to follow this path, going from a random sequence, zeta, we produce a fake data, a fake prediction, x hat. And we are going to measure with this function how far away are the variance and the mean of this fake data, how far away its statistical properties are from the statistical properties of real data. We calculate its loss with this function, and finally we combine all losses. After combining all losses, we apply the gradients. Now we are going for the embedding train step. It's a pretty similar process. For training the embedder, we are going to correct the weights of the embedder and the recovery. So we use real data, and inside the gradient tape, we are going to follow this path, get its loss, follow this path of the autoencoder, get its loss, combine the losses and apply gradients. So you can see we go from a real data into H, and then from H we follow the way into the supervisor. So we keep on using the supervisor. We measure the loss. Next, from X, we go through the autoencoder. So we are going through the embedder, through the recovery, and we get X tilde. Combine the losses, and we will train the embedder and the recovery. Okay, so now let's go for the discriminator train step. For the discriminator train step, we are going to have the similar process. We are going to follow some paths, different paths, get their losses, combine the losses and apply gradients. So here we are going to separate first the function for getting the loss and then the train step. For getting the losses, we are going to use real data and fake data, random fake data. We are going to use real data to follow this path, and we are going to compare the result with all ones. Why? Because we are going to train the discriminator, and the discriminator should be able to classify real data as ones. So If our discriminator classifies X real data as zeros, we're going to have here a big loss, and we can minimize the loss, so forcing the discriminator to recognize real data. So next we are going to use the adversarial supervised network zeta on random data. Random data is coming from here, supervisor, discriminator, and we are going to compare our result with zeros. If our discriminator predicts fake data as zeros, we are not going to have any error, any loss. It's going to be minimal loss, so not too much to correct the weights. But if the discriminator classifies fake data as ones, we are going to have a big discrepancy here from getting ones compared with zeros. So we will have a big loss at the end to correct the weights. And the last path for calculating losses is going from fake data again, but through the not supervised path. And again, the same explanation. Compare the results with zeros. After following these paths, we get the loss for each of them. We combine the losses. We can try different combinations. We will have to try different combinations and be able to approach the best. And finally, let's define the training step for the discriminator. Just using the gradient tape, getting the losses, what we explained here, and with the losses, to the discriminator we get the trainable weights and apply the gradients using the optimizer. And finally, we are going into the full training loop. For the full training loop, we will use the previously mentioned blocks, and we are going to train always the generator a few times over the discriminator. We define here how many times we want to train the generator over the discriminator. Let's see, twice. And so for each training step, we train the generator and the embedder. We use the blocks we defined previously. We trigger here the generator training. We trigger also the embedder training. And after training both of them, we extract new samples of real data and random data to train the discriminator. And we are going to train the discriminator only when the loss of the discriminator is bigger than some value. Why? Because we don't want to overtrain the discriminator. If we train too much the discriminator, the gradients for the generator are going to be close to zero, so there is nothing to train the generator against. And that's the reason for testing here some values about which is the best for training the discriminator, for stop training the discriminator. We print some metrics, and the training process is done. After training, I'm not going to trigger here the training because it will kill the audio of the recording software. So once it's trained, we can generate already synthetic data. We can use the synthetic data block we defined. If you go up a little bit, you can see that we've got here defined the synthetic data. Exactly. So we use some random samples to generate the synthetic data. Once we've got synthetic data, we rescale using the same scaler we use for the real data, and we can plot some samples. After plotting some samples of real data against synthetic data, we can see here the results. We can plot some more to compare. You can see here that we've got here some in blue real data for injective protocol prices, and synthetic data. As you can see, the synthetic data is softer than the real data, almost for every sample. So the main process is done, and now what we have to do is to check if this data is good enough for our purpose. And for doing that, we are going to follow, as it's described here in the original TimeGAN paper, we are going to follow their procedure. We are going to make some tests, visualization, discrimination, discriminative score, predictive score, to test the synthetic data and take a decision, a measure. Is this good enough for our purpose or is it not? And this is going to be done in another video.